Okay, we're on page 244, about halfway down. Type of function is this. Oh, you can't see it. Page 244 on number 4, what kind of function is that? Is it linear? Is it quadratic? Is it inverse? Is it exponential? It's got to be something. What is it? If you see a function that has powers in the numerator, or variables in the numerator and the denominator, kind is it? Starts with and ends with ational. Did you know that, and you were just not on speaking terms with me?
Yeah.
Oh, okay. Well, it's good to know. All right, so let's copy down that formula and let's figure out what it tells us. Page 244 at the bottom, they give us a number line. Let's change that number line into a coordinate axis. So 0 on the number line is still going to be in the same spot. It's just we're going to read it in both directions because on the next page they ask us to sketch it anyway. Okay, what does this part right here tell us? X minus 2.
Zero is at 2.
Very good. So there's a 0 at 2. What does this and this tell us? X equals negative 1 is an asymptote, and X equals 3 is an asymptote. Make sure you put down twice. It's an important thing. So it says, label where h of x is a 0, and label each value where h of x has vertical asymptote as an a. In the intervals between the points you labeled, indicate whether the function h is positive or negative. Okay, so let's go through the rules for positive or negative. Well, think about it. If we put in 0 for x, we'll have a negative number divided by a positive number times a negative number squared. What is a negative number? What is a negative number squared? So what's the sign of the denominator? So what's the sign of the function at 0? It's going to be down here, right? If that is true, what's going to happen at this point right here? After that, it's going to be above, correct? Think about it. We cross the river at 2. We're below the river here, so after we cross, we must be above the river. Make sense? Okay. Since this asymptote appears twice, what's true on the other side of the asymptote? We're also above. Since we're below here, what must be true over here? We're above. Five, four, three, two, one on how well you understand what I just did, not necessarily that you can do it yourself. Help me out what you don't understand about it.
Where did you get like the last positive and the negative sign?
This one over here.
Yeah, what was that?
Okay. If you recall, at an asymptote, if on one side of the asymptote we're at positive infinity, on the other side we're at negative infinity. So since we're at negative here, we must be at positive here.
And then why is the other one?
Because we wrote the word twice here. If you recall about that magnet that we did, remember how it was x minus 5 squared? On both sides it was positive, right? Because the magnets always attract each other. Okay. Keep talking.
I think I'm good now.
Page.
You don't know where's that?
245, number B. So now they want to take that information and sketch the asymptotes along with the parts of the graph that are near the asymptotes. Don't worry about the parts that are not near the asymptotes. Okay, so here's an asymptote. I'm going to use purple for my color. Would you agree on this side of the asymptote, my function is going to be going up? And on this side of the asymptote, my function is going to be going up because it's a twofer. And the closer I get to that asymptote, the closer I get to positive infinity. Now it said just near the asymptotes. Well, you could pay attention to our yellow lines, but you also can pay attention to the river. At the river, we cross. So if we were up here, we cross here. Do we cross again? Do you see any other crosses? Do you see any other crosses in our formula? So we cross here. So for this asymptote, we must be down, right? Asymptote, we must be down. Everybody agree? That's the only... Eric, you're looking at me like you're not real sure.
I'm just trying to take it in.
Okay. So over near this asymptote, we're going... Now, I had to curve it a lot because, remember, I've got to somehow get over to this point over here eventually. And then on this side of the asymptote, I'm up. Now, it said, don't worry about any spot except near the asymptote. So, how could you use algebra to predict the shape of the graph of a rational function near those asymptotes? Just like we did with the signs, right? Number 5. Oops. So they just had a sketch near the asymptotes. Then this is all gravy. Everybody understand that part of the sketch?
Yep.
I'm going to combine what we know about asymptotes with what we know about end behavior. There must be a horizontal asymptote because we only cross the river here. If we're above here, we aren't going to keep on going down forever and ever, right? Now, I suppose we could go down and go back up, right? But then we're missing a turning point. Okay, same thing over here. We're going to, we've got that page that we printed. What's the power of the numerator of our original function? 1. And what's the power of the denominator? 3, right? X to the first, x to the second, x to the third. I'm looking for our rules. So the denominator is bigger than the numerator, which means the end behavior is 0, right? Remember that page in your notes? Kevin, there's so much to remember. I can't remember it all. Okay? Well, you're going to get a chance to practice it on the bottom of page 245. Without using any graphing technology, sketch the graph of this function. Does anybody need help in factoring this part right here? You're doing it as a group, so that shouldn't be too tough. Okay? So you're going to graph that function go. Okay, Nick is gone. Michael's here, Marlena's here, Gavin's gone. Janae's gone. Felicia's here, Nicole's gone. Eric's here, Phil's here, Grant's here, Connor's here, Eric's here, Laura's here, Madeline's here, Jessica's here, Lauren. Hey, Lauren, were you here yesterday? Okay. Jacob's not here, and Sam's here. Okay, who needs some help? Get the zeros off the numerator, get the asymptotes off the denominator.
Yes. Yeah, that's gonna be. How do you know that one is?
Asymptotes are in the denominator,
Yeah, but
zeros
how
are
do
in the
you know
numerator.
that the other one that you just factored isn't an asymptote? It's an asymptote. Like the whole thing is?
Well, one of those, this is an asymptote, this is an asymptote, this is an asymptote.
Okay.
There's 3 of them.
I thought it was just like the one. I was like,
No,
wait, how do
there's
you know?
3 of them.
Who's graphing on this?
Nope. Well, you could on this one since we use this one. Yeah.
Okay.
I don't know if they all fit there. You okay, Jess?
Mm-hmm.
Yeah.
So
Okay.
these are all of the asymptotes.
Very good. The 0 is at -2.
Okay.
That's also
Oh, so if a 0 is an asymptote, one of us made a mistake.
What do you do if you can factor something out of the numerator and the denominator?
So asymptotes.
It's a whole, so I would write
Denominator
whole
equals
up here
0,
someplace.
But the numerator does not.
We don't know where that hole is.
So
Like,
Did you see that?
negative 3
oh, like,
would be.
Oh, you,
that's zero.
hey, you're supposed to do it.
So if x equals negative 3.
Do you see a problem here? Mm-hmm. Yeah, you can't have a 0 and an asymptote.
Okay. Negative 3 plus 3 equals 0.
So write
your
HOLE
yeah.
there.
Would be a
Okay,
positive.
so
and positive?
Yeah. It's just the opposite, basically.
So then this one would be -2, and this one would be -4.
Yes.
Okay.
So then, how do you like?
how do you do it if you have a hole? Or which part are you doing? Cross off your numerator and your denominator so that you can see that that's a hole.
Like right here?
There. And now put over here at -2, write the word hole sideways.
This cancels out.
Yeah. Because it's
So then that would be -4 and +3.
And
Yeah.
then, like, how do you actually graph it? Obviously.
Okay, so you have a-
already right
Yeah,
here,
very
right?
good. So do a dashed line straight up the top.
And then this would be negative.
Yep.
Can I just go with
Yep.
this?
Okay. Now remember your asymptote also goes down too, but you know that, right?
Yeah.
But how do
Okay.
you know if it's positive or negative yet? Do you have to graph that first?
Okay, so it's possible, since you've got a hole at -2,
Or how do you know that?
The whole is because
Those
negative
two
2
cancel.
makes that
Mhm.
both 0, so that would be a whole.
so it could go through 0. It could not go through 0, right? The way to find out is to choose some spots on your graph and see what you get. Like for instance, if you chose 0, so let's say x is 0.
So you put 0 in the graph?
So if x is 0, what's the sign? I don't care about anything except sign. Positive divided by 0 minus 0 minus 6. Negative 0 plus 4.
Positive.
Positive divided by negative positive.
Okay. Positive.
I got a positive number. I'm going to divide it by a positive number times a negative number.
Negative number.
I'm going to have a positive number divided by a negative number means
Negative.
I'm going to be below 0. At 0, I'm below 0.
Okay.
Okay?
So that would be the negative part then.
Right.
So this is
Great. Now, what I would do is choose a point near -4 because of that stupid 0. That stupid hole. I would write hole sideways here so that you know there's a hole at -2. Don't write it in yellow.
what color should I write it in?
Well, it's just you aren't going to see it then.
Yeah, I am.
Okay.
I don't have old eyes.
Ooh. Okay, I'm done helping her. Hey, Marlena.
Yeah.
Now that I'm going to totally ignore her. -3. So try -3 because that's close to that other vertical asymptote, right?
Yeah.
Okay, it's beyond the 2, it's before the 4. So try -3. So if you put -3 in there, -3 plus 2, you're still negative, right?
Yeah.
Positive 9 plus,
Wait,
3.
where'd you get the 9 from?
because I squared 3, negative
Okay.
9.
Oh my goodness.
I don't know where any of these numbers are going from.
We chose 3.
Okay.
-3, excuse me. So the top is
You're putting it
negative.
into this?
Yeah, -3 makes this positive or negative.
Mm-hmm.
This is positive plus
Negative.
plus a negative makes it a positive, right?
Yeah.
Okay. -6, you're still going to be a positive number.
Mm-hmm.
-3 plus 4 is positive. So you have a positive under a negative. So it is negative, right? So here it's negative, and on the other side of your 0, it's negative.
Okay, so you can just use like any number.
You can choose an easy number though. Don't choose 4.13846. Because that's, just choose a whole number. Okay. So here's the things that we ran into when we were graphing this. K of x equals x plus 2 over x plus 2, x minus 3, x plus 4. And as we started graphing it, some people forgot about the poles. And so they said, well, I've got an asymptote 0 at negative 2. What I told them to do is to just write hole at negative 2. There's a vertical asymptote at negative 4. There's a vertical asymptote at positive 3. Did I miss a power there someplace? No, I didn't. Did I? No. Okay. Now, what we found out then is what are our values at any spot. I always like to choose 0 because 0 is easy to substitute in. This is positive if you substitute in 0. This is positive. This is negative. This is positive. Positive times a negative times a positive is a negative. So you have a positive divided by a negative means that at 0, we're below the graph. Or we're below the line y equals 0. Question. Menominee, you got to talk. You're softer than Chippewa right now.
Whoa.
Thank you. Okay, now one of you had a question? Who was it? I thought I heard you guys ask a question. Nobody did? Okay. So how are you on finding the sign of what your function is at any spot? So we're just below the line at this spot here. Now, we didn't cross here at the anywhere between here and this asymptote here. So over at the asymptote, we will be negative here, which means we're going to be positive here. And it didn't ask us for our end behavior, but it's going to be like that, correct? Now, because there's a hole here, some people say, well, maybe the hole was at 0 and we did at 0 and we did cross. So that's why I said, well, let's try finding a number over here that's between negative 2 and negative 4. And I said, try negative 3. Well, negative 3 plus 2, that's positive. Negative 3 squared is 9. Minus negative 3 is 12. Minus 6, that's still positive. And then negative 3 plus 4 is still positive. Did I make a mistake?
Yeah, negative 3.
This is negative on the top. So I have a negative number divided by a positive number means I'm going to be negative over here also. So wherever this hole is not going to affect our graph as far as positive negativeness. And so we're going to end over there. Now, some people did graph it. I don't know. I thought I saw somebody graphing it. And the thing is, are you going to be given a demerit for writing or for graphing it? No. So let's look at what it looks like. Okay, so our function that we graphed is this one, right? And if you notice, it does not cross in the middle part there. And if we go to -2, wow, I got to zoom in to get to -2, huh? If we, oops, I just saw it. -2, it is indeed undefined. Our assignment said only pay attention to near the asymptotes. Page 246. So let's pretend. Let's pretend you got this graph. Let's pretend that all of the important parts are listed. In other words, nothing happens to the right of 8, nothing happens to the left of -2. It doesn't show any holes, so let's not make any holes. Go. Make the function, just like I did here. K of x, start with the function. In other words, we made the graph from the function. Start with the graph and make the function.
I just have a whole side. I don't, but that's my guess. Where'd you get that? I know there's a hole there. There's no more circles. Just two crosses. Oh, does that mean it's a hole then? Something that's nice. Okay. Yeah, because the little dot ones. Oh, what holes always be on top. Oh, yeah, because see up here. Is that okay? We'll shoot for this one.
Say what they said.
No, but yeah, so this would have to equal 0 and 1 and the bottom. Okie dokie. This is the other head.
That's mouse. That's mouse. That's not
Same.
Everybody ready? Okay, let's go through it. Numerator, x minus 2, 1, 0.
Oh, you got it.
Denominator, x plus 1 twice.
Oh.
X minus 1, x minus 3. Now I heard a bunch of people say, oh, because they realized... What did they realize? It ends on the same side of the asymptote. Both going down. Numerator power must be less than the denominator power. How do you know? Because it has a horizontal asymptote at 0. So this can't be x minus 2 to the 7 or something like that. Okay? It's only going to go through this 1 point one time. I suppose it could go through 3 times. Could it? 1, 2, 3? Yeah, it could still go through 3 times, but it's not going to go through it 7 times. Here we go. Page. $247. Oh, you're getting very sleepy when administering a drug such as an anesthetic. So, you know how somebody had asked the other day, I went to the intranet and found it for myself. Where did I put it? Let's see. The internet. Didn't put it there. Oh well. APA marijuana guideline. They had a really long article here, but they do have a statement on marijuana use. Marijuana guideline, maybe. There it is. Position statement on marijuana and medicine by the APA. This is the one that I thought you should read. There is no current scientific evidence that marijuana is in any way beneficial for the treatment of any psychiatric disorder, which I suppose means that it could be, they aren't saying it's not useful for treating cancer. You know, when people they react to cancer chemotherapy. In contrast, current evidence supports, at minimum, a strong association of cannabis use with the onset of psychiatric disorders. Adolescents are particularly vulnerable to harm given the effects of cannabis as neurological development. The reason why I did this is the Eau Claire City Council met yesterday and decided to make the fine for marijuana use or marijuana possession $1. And then one of the guys comes on and he says, dude, we should make it 0 because you don't get a fine for consuming alcohol. And this is no more dangerous than alcohol. Obviously, he is not paying attention to the APA, the American Psychiatric Association. And the thing that you have to understand about mental illness is, it is like when you see it, it just makes your stomach just turn because some of the people have just
like huge issues that are affecting their lives. So much so that like they can't even function. It's just you just become so thankful that you are normal. Now don't say I'm not normal. I don't want to hear that. I heard you snickering. That was at least a snicker. Oh, there's a head bob now. Now I see. Okay, here we go. Here we go. When administering a drug, such as an anesthetic, it can be useful to have an accurate mathematical model of how the concentration of the drug changes in the body over time. One question that might be answered is, using this mathematical model, might be, how long does it take the anesthetic to take effect? Has anybody ever had an anesthetic, like for instance, they had an operation where they totally knocked you out? Because I've had Novocaine. Okay? How long did it take till you were totally knocked out?
Very long.
I think they counted back. They told me to count backwards.
They gave me like fentanyl, I think it was one time. It didn't even take it. I think
Yeah.
I said dose 2 and that was it.
Yeah. I think I started at 10, and I think that was the only number that I said. Apparently I'm easy to knock out. I don't know.
I just don't know how to count. So.
I don't know how to count. So she stayed awake the entire surgery. All right. So how long it takes to start down that process. But the other one that's equally important is how long it takes until, or how long you stay in a sedated state would be an important aspect too. Okay. Let's see here. Experiments show that the concentration in nanograms per milliliter of a certain anesthetic T hours after administration can be modeled by this function down at the bottom of our page. Part A. We're going to talk about the short-term behavior of the function. A. The patient is considered to be under full sedation when the concentration is above 250 nanograms per milliliter. They say, during which period of time does that take place? You could use algebra to solve it, right? But I think in this case, graphing it in Desmos will be a much better solution to our problem. So let's graph it and see what we get. I can go to my office and get another pair of readers because the screw came out of these and I don't know where the screw is. And I can't fix them and I certainly can't see without readers. So work on it. Do A, B, and see if you can figure out number 3 also while I'm gone. I'll be back. But make sure you graph it because I think that's the best way to solve those.
His breathing just froze my ass because I almost glass.
Who's one class, the other class? So, yeah.
Well, yeah, we are, but is anyone actually going to do it now?
Sit here for 2 hours.
Sorry, there's always next semester for college.
I was going to say, I'd be like, yeah, I don't know what I'm doing. And he'd be like, yeah, that's unusual, so. Yeah, I found the first thing she does is come over.
Same.
We don't talk to anybody else.
It is for her. And so she's like 50. And she has
The kid next to me has me, so.
Any of those?
I'm supposed to be just well on the test.
Well, the thing is, right now, I still have to fail. I failed the Because I was like 69 assignments behind, and now I'm probably like 30. But he
Finish my last.
he's like, yeah, I haven't started, but I had an F in
Okay
that
with
portion because we hadn't put them all back in yet. The ones that I completed, and so it's his F.
Not too worried about
It's I wonder how much he has.
Yeah.
looks like that.
Yeah.
That's not.
We got like almost the same stuff on the test. One or two, one or two elementary
Oh.
It'd be weird to see what he has over
Like it says I have over the it's like a trait. Yeah, that test or whatever. And then it says I have or like the test portion and then my score. And I'm like, so my homework and not really, because you're in class. It makes your class stuff is only 10% due, right?
Stout, yeah, they make in class.
Yeah, and then the other stuff is,
I think like your,
and then your test is like 85% cost.
yeah.
There's 75 to 85%.
And then is not, I thought the homework was.
Yes.
I can sell shades, but I don't know how good that's going to be.
But attendance is like 10%. Yeah.
Which I'm like, wait, is it the homework?
The homework might be better. Yeah, I can't understand all the shit.
Well, I just did this homework.
That's right.
Because I'm shooting for the well, so then you know, 3.3 the GPA.
Set up a tent by myself.
And I somehow had an A in the intermediate class of algebra before this. No, it wasn't. It definitely was not easy for me at all. Like literally, that's why I've had this high school kid doing all my homework from last time and this class. Like I'm not even joking. This is
Plus it'd be
really
like a
freaking
nice
hard.
like creator. It's the same actually.
Like I struggle a fuck ton with this class. Like to the point where I can't. That's why I had to pay somebody to do my
Oh, hours.
What do you?
Well, Kevin's
What is this? Is that scary? I remember I touched it.
Okay.
I almost wore my jeans. Yeah.
So on our graph here, they say 300 t squared over t to the fourth plus 16. And then it says when the anesthetic is above 250 nanograms per 250. Oh, I see. I've got way too much time there. That's the problem. I gotta change my x-axis from, let's say, 0 up to, say, 12 hours. That might be a better. And then the y going from 0 up to, what did it say, 250? So let's say 300. So when is it above 250 nanograms per deciliter? So from the beginning, oh, I'm graphing the wrong one here. Let's go up here to this one. There we go. So 250, if we put that line in at 250, y equals 250. So it's above 250 from 1.236 hours to 3.236 hours, or a total of 2 hours. Part B, at what time does it reach its maximum concentration? Well, when I clicked on the graph, that also appeared, and it reaches the maximum at 2 hours. And what is that maximum concentration to be?
375. Did you guys get all those answers, or were you too busy talking and didn't get them done? Did you graph it? Did you get those answers? Girls?
I graphed it.
But you didn't get the answers. You didn't know where to click, or what happened?
I don't know. I just
Didn't graph it.
I didn't graph it.
Why was he like that? I can't believe it.
Because you gave me the look. I didn't graph it, dude. Laura, you okay? Jessica, you got it? Lauren?
My graph looks weird.
That's probably because of the window.
Okay.
Window. You could try window fit.
Oh, that's a calculator. Oh.
You have to go for X minimum goes 0.
Okay. Oh wait. That's okay.
And then X maximum goes, say, 10 hours. And then Y minimum goes 0. And Y maximum go 350, I think. Or 3. Yeah, go 400. And then it'll look a lot closer to mine.
Oh, I got it now.
Okay? All right. Keeping on going. Then it says, let's analyze the long-term behavior of this function. There are 2 test questions on the next test that people get wrong like crazy because they don't understand what it means to analyze the long-term behavior of a function. So we've got the graph there. If we go farther towards the negative here, we will eventually get to a certain spot. If we go farther towards the positive, we will eventually get to a certain spot. Some of them you don't need to graph. Like, for instance, how much drug was in your bloodstream 1 million years ago? 0, right? Does anybody still feel the effects of the last time they were under anesthetic? No, you got how much in your blood? Butt kiss, right? So it's going to be 0 in this case at both extremes. You don't need to graph it. But if you were to graph it, it shouldn't surprise you that the closer you get to infinity, the closer the amount in your bloodstream will get to 0. Now, one of the things that I'd like to show you is this graph is perfectly symmetrical. And the reason it's symmetrical has to deal with everything is to an even power. Well, if you consider 0 to be an even number, to the second, to the fourth, to the 0th. Everything is to an even power, so it'll be perfectly symmetrical about the y-axis because, like the square root of 25, 5, negative 5. So they always work out. They always work out that way with functions like that. Then it says, it is not safe for a patient to drive until the drug concentration falls below 20. Well, you look here, it's 20 at a long time out here. About 12 hours, it's still above 20. A little bit after 12 hours, it falls below 20, right? 12 hours and 12.3 hours. It looks like it's below 20. We could make y equals 20 and see that the address of that point is 12.243 hours. Now here's some math that some people don't know how to do because in my math lab, it'll say convert 20.243 hours into hours and minutes. Everybody agree it's 20 hours, right? So we're going to take 0.2243, that's the decimal part, but how do we convert that into minutes? Anybody know? 0.243 hours times 60. Very good. And you get about 14 and a half minutes. Does that make sense? 0.245 is close to a quarter. A quarter of an hour is 15 minutes. Okay, next. What value does the function approach? This is kind of like the test question. What value does the function approach over very large values of time? It gets closer and closer to 0, right? What does this mean in terms of concentration in the person's body? They get less and less until essentially there's none left in the bloodstream. One of the things that you notice about this function, 300t squared over t to the fourth plus 16, is that it's always positive. In fact, you will find that for every drug intervention model. They will always be positive. How come? Because you can't have negative drug in your blood, right? Everybody agree with that? Okay. Next one. Sometimes a treatment plan may require maintaining a steady concentration of a drug over an extended period of time, and one way of doing that is through an IV drip. Suppose that the resulting drug concentration from an IV drip is given by this function. C of t, C2 of t is 5,000 t squared plus 450 t to the fourth over 3 t to the fourth plus 20. Now I think they kind of tried to disguise what was going on here with the way they wrote it, but we'll go through it just exactly the way they have it. Use the function to answer to the following questions. What is the maximum concentration that the drug reaches, and when does this happen? They didn't say graph the function, right? They didn't say solve the function. All they did is they gave you a question. To me, the best way to answer that question is to graph that function. And so I'm going to do that. C2. Okay? Notice it's also symmetric, but it's pretty easy to see that the maximum concentration is reached at 1.8 hours. Since for my math lab, they asked you to write your answer in hours and minutes. So for question 4A, change 1.803 hours to hours and minutes. Go. And what is that maximum concentration? 406 nanograms per milliliter. Part B. What will the drug's concentration in the patient's body be after a long period of time? So let's say 1 day or say 2 days later. the gut drug concentration gets really, really close to how much?
0.
It doesn't look like it.
Oh.
What is that number? 150. Part B. So the limit, I'm on page 249. So the limit, as time approaches infinity of the concentration of the second drug is 150. So the longer time goes, it gets closer and closer to 150. So if you see a limit, you can graph it and you can find out what you're going to. In this case, it says as you go to infinity. But if it were, say, as you go to, let's do this one back here. The limit as for f of x, as x approaches -1, it approaches negative infinity, right? As you get closer and closer to -1, the graph just keeps on going down and down and down and down. Okay. Why was it 150? If you look back at our rules for asymptotes, the power of the numerator equals the power of the denominator. The power of the numerator equals the power of the denominator. And when that's so, we take the numerator's leading coefficient divided by the denominator's leading coefficient. 450 divided by 3 is 150. So that's our first experience with this kind of thing. Now, why does the drug stay at 150? Remember, what are they doing? They're keeping that person on an IV drip so that the drug stays at a certain level. The mathematical model that they wanted it to stay at was 150. They could have chosen anything, but they chose 150, and so they had to drip it into the person's bloodstream at such a rate so that the concentration over time stayed at 150. Got it? We'll take our break. When we come back, we'll go through the rest of these on 249.
You're trying to understand what's going on.
How long have you been out there?
Just a couple of minutes. That's
Oh,
why I
okay.
was waiting.
Okay. Oopsie daisy.
That's a mess.
crying.
No, it's, you have the arm-like one, right?
Yeah.
It's like chat.
It's just like crazy people
Okay.
understand stories.
Match
I like that good video.
That's fine.
They're like, "Will forever be one of my favorite songs." And I'm like, damn it. Oh, I'm crying.
Go on search. Push that in.
It's so cringy.
Well, it's just
That's my thought process for it. You know, are they like, I'm not gonna have any time to do the best we can because we're kind of through. No, I keep the seeds. I ride that. Let it get out. Keeps me at 3.33. Yeah, me too.
Okay, let's get started. So if you look at page 249, we've got these limits. And the part to pay attention to in this first one, remember, is just the powers. So the power of the numerator is smaller than the power of the denominator. Did anybody not get this page copied into their notes yet? If you didn't, make sure you take a picture of the screen or something so that you get it into your notes. So which case is this? Numerator is smaller than the denominator. First one, right? Which means the end behavior is 0. Next one. So the limit as t approaches infinity of that function is 0. Write a sentence describing the behavior of C4 for large numbers. As time gets bigger and bigger, the concentration of C4 gets closer to 0. Did Laura have to leave? Okay. Didn't want to lock her out. There are some students that don't mind locking out, but I didn't.
What's that mean?
Okay. Page 251. A manufacturer wants to reduce the amount of pollutants it releases into the environment during its production process. There was just this last Friday, in fact, the 17 or 13 different government agencies came up with a statement about pollution. Anybody know what it was? Global warming has its origins in human activities. All right? And President Trump came on and said, we've got to do stuff to take care of the environment. Well, why are we not doing more? Does anybody know?
People are lazy.
And they don't want to spend money. And that's really what this activity is about here. Because it says, what should the manufacturer consider when developing a pollution reduction plan? Well, it's got to consider how much can it afford to cut pollution. Because at the same time it's cutting pollution, there are people saying, I need more money because I work here and I'm important, at least to me. So I need more money. And then there are other people that say, we need to collect more taxes because we have government programs that we need to fund. And so your company has to pay more taxes. Well, you see how there's only so much money to go around. You can't just like make it up out of, well, you can. They call it a printing press. But ordinarily, unless you're the government, you can't just make money out of nothing. Here we go, the two plans. Plan 1 removes P1 times X percent of pollutants, where X is the cost in thousands of dollars. Plan 2 removes 160X over 5 plus 2X percent of the pollutants, where the cost is in thousands of dollars. Now, we could be thinking about vertical asymptotes and zeros. Does it make sense that one of our zeros is 0? Yeah, if you don't spend any money, you remove no pollutants. Okay, so that's our zeros of both numerators. Asymptotes in the denominator, if you spend negative $6,000, right? Which, that doesn't make any sense. Okay? So apparently that first one is that it's going to be going up as we get closer and closer to 0, and then at 0 it's going to be 0. Okay, plan 2 has a vertical asymptote at negative, 0.4, and a 0. So it's got a vertical asymptote at negative 0.4 and a 0 at 0. So I would start by graphing the two functions. Plan 1, plan 2, and here they are. And if you notice, I didn't need to graph higher than 100%. How come? Because I can't remove 200% of the pollutants. Well, you should try harder. Then you could remove 200% of the pollutants. You're not trying hard enough. No, you can only remove 100% of the pollutants. So you see both of them graphed there. Does it appear that they have an end behavior that is the same on the right-hand end? No, they don't have this end behavior the same, do they? The green one can remove more pollutants than the blue one can. Let's go through the questions on the next page and answer them. Question 1. If the manufacturer is willing to invest $10,000, so we're here at 10, so X is 10. If it's willing to spend $10,000, which plan will remove a greater percent of the pollutants? So I'm going to zoom in here at, that didn't work so good. I'm going to zoom in here at 10, and which one removes a greater percent of the pollutants? The blue one, right? Which is plan 2. Plan 2 removes more pollutants than plan 1. B asks, at what level will they be the same amount? Well, if they both spend $11,500, they will remove 65.714% of the pollutants. Now it says, how much does it cost to remove 90% of the pollutants? So I'm going to turn off this line and turn on this line. So now I'm at 90%. How much does it cost to remove 90%? Well, if you notice, plan 1 can remove 90% if you spend $54,000. Are you writing those down? Plan 2, how much does it cost? You can't remove 90% of the pollutants with plan 2. It can't happen. you've got to understand the limitations of mathematics. If you come to me the last day of the semester, you've done no homework, you've done no tests, you never showed up for class, you ask, Kevin, what can I do to pass this class?
Nothing.
Nothing. Okay? Now, you get to the last day of the class. You've gotten an A on every single assignment, an A on every single test. You showed up for class every single day. You say, Kevin, I'm worried about passing this class. I'll say to you, don't worry. Now, you may not get an A, right? Because if we take that last test, you aren't going to flunk, but your grade probably isn't even going to be lower than a B+. Okay? Mathematics can't solve some problems. The process that they chose for pollution removal plan 2 will not remove more than 80%. Why 80%? Let's look at the leading coefficients. Why is it 80%? What math are you going to press on your calculator? 160 divided by 2 is 80. Pay attention to the leading coefficients to solve your problem. So, if that is true, if you're willing to spend a great deal of money, you decide how much. Which plan should you use? Plan 1, because Plan 2 will only remove 80% of the pollutants, no matter how much money you spend. That is called a horizontal asymptote, or the end behavior. Okay? So here, what's the horizontal asymptote? Y equals 4. How about here, horizontal asymptote? Y equals 0. Very good. Do you see why it's 0? Because the denominator power is bigger than the numerator power. Last one. Y equals, what is that, 6 2/3? Because the power of the numerator is squared, the power of the denominator is squared. So what do you get? Right? 6 2/3? Page 253. The graph. Let's sketch the graph. What's the address of the vertical asymptote? You could go to Desmos if you want to, but by now you should be able to do it just from the equation. Oh, I have it on the wrong spot. Sorry about that. X equals 2. What's the address of the 0? X equals negative 2/3. Because if you take 3x equals 2, negative 2, x equals negative 2/3. I got it from the numerator, right? Horizontal asymptote at y equals 3. Take the numerator power or coefficient divided by the denominator coefficient. So since it goes through this point here, it doesn't cross this line here, our graph is going to come from that negative infinity, go through this point down to this asymptote. What happens on the other side of this asymptote? Positive infinity, right? Now the only question is what happens between here and there. Sometimes it'll go down through and then come back up, and other times it will just go out like this. And so you don't need to know the math for that. That's why graphing it at that point wouldn't be a bad thing to do. Here we go. There's the graph. This time the graph just comes down and goes all the way over to positive infinity. Graph the function. Page 255, food costs. In 2012, the United States consumers spent $695 billion. China spent $779 billion. French spent $193 billion. Is this enough information to decide which of these countries' individuals spent the most on food? So that's how much the country spent. Could you tell which one spent the most on food? Per person. No, because you don't know how many people lived in each of those countries. So they say, here's the information on the people in each of those countries. So let's do the US, let's do China, and let's do France. US was 695, 288, and then I'm going to just use the letter M for million. Dollars divided by 313.1 or 0.9 million. China was 779,180 million divided by 1,350.4 million people. And then for France, it was 193,153 million divided by 63.6 million. Now, the reason why they wrote those as 695,000 million is because they wanted you to be able to cancel the millions so that you know what you can enter on your calculator. So the millions cancel here, the millions cancel here, and the millions cancel here. Since that's true in every one of those cases, on our calculator for the US, we just need to press 695,288 divided by 313.9 and find that the US spends $2,214 $15 on food per person per year. China, what'd you get for an answer? They only spend $577 on food, and France, $193, $153. Oops. Divided by 63.6 is $3,051 on food per person per year. Now, I'm going to ask you a question. So does that make sense for you? Do you spend $2,215 a year on food? That'd be about $40 a week per person. Raise your hand if that's about what you spend. Okay? More than that, raise your hand. Less than that, raise your hand. Okay. Yeah, I think that's kind of an underestimation. Okay. So, that's how much they spent in whatever year that was. Don't remember the year. 2012. Page 256. Food expenditures in the United States between 1988 and 2013 can be modeled as follows. Expenditures as a function of time is 44.419 t squared plus 7855.5 t plus 480926. This is E is in millions of dollars. T is in years. So in 1988, the United States spent $480,926,000,000 on food. How do I know that? Because T equals 0, right? What happens to the first part of our polynomial when T is 0? Becomes 0, right? Second part of it when you becomes 0 also, right? So all that we're left for 1988 is that amount. For this problem, and then population as a function of time is 3.0245 t plus 240.02. So in 1988, there were 240 million people in the United States, and it grows by about 3 million per year. Food expenditures grow by about 78,500 or $7,856 per year. Let's graph those two functions. Food costs, here we go. So there's, I'm going to zoom out here a ways because I have to get both functions on the same graph, and I don't know how I'm gonna do that. I'll go vertically up to there. Yeah, I'm going to take. The problem is, if you notice, the population is growing so much slower than. I got to change this to Let's go out, say, 50 years. And let's go back to 1988. No, let's go back 10 years before 1988. So there you see, remember, this is the expenditures, but the population is way down here, which makes sense because remember, each person spends about $2,000. So to get those on the same graph, you can see that the population is hardly changing at all. The expenditures is the one that is changing a lot. So that's what they're trying to show. Determine a formula for the function f that models the amount spent per person t years after 1988. Let's look at our function and let's make food as a function of time is the amount of expenditures as a function of time divided by the population as a function of time. So we just need to put this formula on top and this formula on the bottom, and we will have our food expenditures as a function of time. 3.0245 t plus 240.02. Numerator is 44.419 t squared plus 7855.5 t plus 480,926. So there's our food expenditures as a function of time. I got to remember to mark Nick present, and I'll just change it to, I'll use tardy for half the day. And who left at halftime? Laura, and who was the other one? No, in Menominee, somebody left.
Grant.
Grant did? Okay. Okay. Okay, so we've got that graph, and we can model that in Desmos. And the easiest way to do it is to just grab this part of the first equation and put it on top, grab this equation and put it on the bottom. And now when we graph it, I'm going to turn these two off because we only want the food function. And if you notice, it makes sense. We aren't going to have $200,000 of food expenditures per year. So let's go this back to, say, $5,000. Okay, and our y-axis, let's go back to 0 because we aren't going to be spending less than 0. So there's our function, and it looks pretty close to linear, doesn't it? But can you see that it's kind of swooping up a little bit? What amount was it per person per year in 1988? $2,003.69. How about this year? What would the expenditure be? Well, we're how many years after 1988? 30 exactly. So at 30 years, we're at $2,287. How about in 2025? So that'll be 7 more years, right? Year 37. In 2025, it will be $2,365.24, right? How fast is food cost rising between year 20 and 25? So I'm going to put those 2 years onto our graph. And now let's calculate the slope. how do we calculate slope? Take 2,233.849. We should do it in parentheses, right? Parentheses, 2,233.849 minus 2,182.302 divided by, I'm going to just press divided by 5 because that's how many years there were, right? What'd you get for an answer? Well, I don't know. You wanted me to do it too? Geez Louise, people, I already passed college algebra, okay?
Gosh, that makes one of us kind of.
You want to keep it that way? Keep not doing what I tell you to do in class, and you will succeed in not passing. How much did it rise per person per year? About $10. Each year they do a Thanksgiving, like how much does a Thanksgiving meal cost, and it'll say the price went up so much or down so much. So the thing I like about this is that it's taking into account the population grew. That's not why the cost went up. The cost went up because I can think of a couple of reasons. Inflation is one. It'd be about 2%. No, 2,000. Let me think. $10 per year out of 2,000. That's about 0.5%. So it's not inflation. There's other things that are going on besides inflation. Okay.
My 600-pound life.
Now, number 3. On that page that we wrote long-term behavior before, end behavior. Remember, horizontal asymptotes only deal with situations in which you are a long ways away. So we had the graph, and we just kept on going farther and farther and farther and farther into the future. So if we look at this graph on this page, let's make it go not out to 50 years, let's make it go out 500 years. Do you see what happens as you go out 500 years? It just keeps getting more and more and more. Now, you say it keeps getting steeper and steeper and steeper. Let's go out.
Of course, if they go straight up.
I'm going to make the y-axis go up to, say, $14,000. Does it look like it keeps on getting steeper and steeper and steeper? Let me go out, say, instead of 500 years, 5,000 years. Okay, so then I better make my y-axis go up to, say, $100,000. There we go. Did you say it keeps on getting steeper and steeper and steeper?
Now it looks like it's increasing linearly.
It looks like the farther out you go, the closer it gets to a line. Let's look at our notes that we had. I had you copy down these notes on purpose because we are now in the one case we haven't talked about. And that case is if the power of the numerator is exactly 1 bigger than the power of the denominator. Isn't that the case here? What's the power of our denominator? What's the power of our numerator?
2.
If that is true, just take the leading coefficient of the numerator, which is
44.419.
divided by the leading coefficient of the denominator,
3.0245.
and you get 44.419 divided by 3.0245 tells us that eventually the cost per person will even out at $14.69 per person per year. How fast is this function increasing between t equals 490 and t equals 500? $14.68 per year. Between 990 and 1,000? $14.68 per year. How about in that period that we did on our math that we just did on our calculators? It was increasing only $10.31 per year, right? But eventually, although at the beginning our graph was going up, eventually it just became, like Maddie said, became a line. So there is a curve here on this end. It just keeps going up after that. That's called a slant asymptote. Now, the limit as t approaches infinity is infinity of f of x is infinity. That's true. It's just going to keep on going up and up forever and ever. But we can tell what its rate of change will be. And that's the important thing. Page 257. The graph here has a slant asymptote. What is the slope of that slant asymptote? Well, you take the lead coefficient of the numerator, 4, divided by the lead coefficient of the denominator, 2. And so we can draw a line that has a slope of 2. Okay? And our graph is going to be on one side of it, then on the other side of it. And we've got a vertical asymptote at 0. The only thing you can't figure out yet is where this crosses. That part is difficult for you to figure out without long division. I've tried to teach you long division before, and it caused me to go a little bit stir crazy, so I'm not going to teach you long division. I am going to tell you this. Dang it, those grade school teachers that say, oh, you don't need to know long division because you can just use your calculator, are wrong. You can't use your calculator to do long division of polynomials. Page 257. Find the slope of the slant asymptote. What did we say? M equals 2. So, part A here. We have to decide for each one of these. Let's do all of the stuff that we can find out, because then we're wrapping them up. Page 257 and 258. For every single one of these, f of x equals 3x cubed minus 2x squared plus 1 over 2x squared plus 6x minus 5. The first thing that I want to do is, well, I mean, I could just graph them, but I want to find the zeros just in case there are any. So I'm going to use my apps, my polysimul 2, and I'm going to find the roots of a third order, and I'm going to press 3 is the first coefficient, 2 is the second coefficient, 0 is the third coefficient, 1 is the fourth coefficient, and it gives me only one real root. For my denominator, I'm going to go back to the main polynomial root finder, go back to second order because this one is a second order polynomial, 2, enter. 6, enter. -5, enter. Solve. And it tells me my roots are at x equals -3.67 and x equals 0.68. I guess it was -0.368. So now when I graph this one, I have a 0 at -1. I have an asymptote at -3, an asymptote at positive 0.68. I've got a slant asymptote that has a slope of 3/2. Part B. F of x equals 2x squared times x squared plus 6. I have a 0. I have a double 0 twice. In the denominator, it's x plus 3, x minus 3. So I have a vertical asymptote at -3, vertical asymptote at +3, and I'm going to touch at 0. This time, since the numerator is bigger than the denominator, I have no horizontal asymptote or slant asymptote. So my graph is just going to keep on getting bigger and bigger and bigger as I go past those asymptotes. And in this case, it's going to end going up because my leading coefficient is going to be positive. So it's probably going something like this, then like this, then like this. Yep, because it's got the same power on the it's got an even number of powers in the numerator. Last one. Four x times x minus 1 over x plus 1 x squared minus 3. The 1, 2, power of the numerator is 2, power of the denominator is 3. So it's going to have a horizontal asymptote at 0. It's going to have zeros at 0 and 1. It's going to have vertical asymptotes at -1 and positive 1.7 twice. No, let me think. Yeah, 1.7 twice. X squared minus 1, or minus 3. Nope, and at -1.7. No, or the horizontal asymptote is at 0, so it's going to come in like this, and somehow go back up through that. Don't know how that's going to work. I'm down here. Oh, I see. I didn't get the asymptote right. Should have had it going like this, down, up, and then on this side, up, and then over. Page. $259. The following graph
of this rational function is given. What do we know about the graph? We've got vertical asymptotes at -2, -1, +1, and +4. We have zeros, so that would be at 0, and then one more someplace between like 1 and 4. We've got a horizontal asymptote at 0. When we sketch the graph, put in the asymptotes, -2, -1, +1, +4. Put in the zeros. There's 1 0 here. The graph goes like that. Oops, I zoomed in too far. On this side of the asymptote, the graph goes like this, crosses over and goes up. On this side of the asymptote, it does the same thing, goes up. We don't know what happens in this section here, but over here, the graph goes to infinity. So the two parts that we're going to be talking about tomorrow are what happens here and what happens here. Is there nobody that shows up next period in your campus? Menominee?
Here?
Yeah.
No, there's another class.
Oh, there is. Okay.
See you tomorrow, Kevin.
See ya. See you guys.
Got like 12 kills.
Nice. Guys, coming down territory.
Yes. I'll kill him over. Wait for him to screw up. Joel.
What about the guy in green?
Oh, I'll get him. Kill the purple guy real quick. Kill him real quick. What are you doing?
Jeez.